Okay, now we're great. And we were, let me put this down. And come on. So there's one slide that I didn't, the math of it last time, or I didn't understand the math. So I rewrote the slide to make it agree with me, I think. But maybe we're missing something. But yeah, so this was simple, right? Where were we? We were
to 3-level paging. 8.51.
Which slide did you change?
wait,
You changed something that we did already?
yeah, I think I did. Wait a second. Yeah, here, I changed this slide. I changed this slide. You'll tell me if my changes make sense. So we said like this. This is, remember we said we can divide this address. I'm going back a little bit. We can drive this, we can say 10 bits for, in other words, okay, let's start slowly. Page offset is inside a page. How many addresses there are in the page. That's always the easiest thing to remember. I always remember that. That's the way you start with. Then this whole section over here is the page number. But we can, so theoretically our page number is these 22 bits. And that means we have a lot of pages. We have 2 to the, right? We have 2 to the 22 pages, which is 4 megabytes of pages, 4 mega pages, not megabytes, 4 mega pages, right? 2 to the 20th is a mega, so 2 to the 22nd is 4 megabytes, 4 mega pages. But we divided it up into 2 sections. And we say, since the page table is paged, the page number is further divided into a 10-bit page offset, assuming each here, I think I added this also, assuming each row, right? I added this, Zava? Are you?
Yeah.
Yeah, I'm just putting in our assumptions here to make it clear. Assuming each, this is important actually to understand, assuming each row in the page table is 1 byte. Assuming each row in the page table is 1 byte, so then, why is that right? A 10-bit page offset. In other words, if we want to, what is this 10-bit? What is this page offset? This is the blocks in the page. In other words, in the page, in this picture, right? This is a page table, right? In other words, if each row here is there's 10 bits of rows here. 2 to the 10th rows in this table. That's what this means, that it's 10. Yeah, does that make sense? Do I have some agreement? We're trying to describe what's going on here. How big is this and how big is this? It's got to have some size. So what I'm saying is this is 2 to the 10th. Not 10 rows, but a lot more than 10 rows. 2 to the 10th rows. And each row I can choose by these 10 bits here. That's what's telling me every row in this page. What do these 12 bits tell me? This tells me how many rows are in this page table. This one has 2 to the 12th rows. But on one thing one thing we have to think about is
Lisa, how does that change what we saw 2 slides later with the offset and the encompass number?
right. So I want to think about this. So why Why did I write that? Why did I write that each row in the page table is 1 byte? In other words, if it would be more than 1 byte, what would be the problem? Well, let's go on and we'll come to that again. A 12-bit page number, we will only have 4 kilo pages in our page table. In other words, this is telling us how many are in the outer row. So this is our logical address, where P1 is the index into the outer page table. P2 is the displacement within the page of the inner page table. This is known as forward mapping. All right, let's see this again. So the P1 is telling me this section is saying which row in this table to go to. And I've got, what did I say? 2 to the 12th. And this P2 is telling me how, here is the key point, how far down to go. You see, if this wouldn't be 1, now I'm going to answer this question that I asked you. If this wouldn't be 1 byte here, if it would be, let's say, 4 bytes. Let's say each row would be 4 bytes and I'm still using 10 bits for the offset. Then what's wrong with this picture? Look, what's wrong with it is this part here. What's wrong with this part? Remember, this is telling me, the P1 is telling me how far down to go here, right? And also the P2, that only makes sense, even this one. This only makes sense if this number is referring to bytes. Because if each row here is 4 bytes long, then the P1 is not going to tell me how much to go down. I'm going to have to multiply, I'm going to have to add 2 zeros to it, right? I'm going to have to multiply by 4. If it's saying 1 over here, it doesn't mean to go down 1 byte, it means to go down by 4 bytes, if each row is 4 bytes long. But assuming I'm not doing any multiplication and I'm just taking this number like it's written here in this picture, then every row here must be 1 byte. Otherwise, this picture is wrong. See that? And so to here, every row here must be 1 byte. So how are you with me?
So the number is.
Otherwise, this P2 won't tell me how far to go down. It'll have to be P2 times 4, or times however many bytes there are.
So what does that have to do with offset?
No, I'm just explaining why I wrote, assuming each row in the table is 1 byte. This is also assuming that each row in the table is 1 byte. I'm just explaining what I wrote.
The number we find in the outer page table is gray chunk. That tells us how far down to go in the page table.
Yes. In other words, we get a number here. No. This number that we get in this row here is telling me which box to choose. Because remember, it looks like this. There are all these different boxes, and they're all randomly spread out throughout memory. I don't know where they are, but I've got to know the number of that box so that I can find it. That number is stored here. In this page table, I've got the numbers, the ID numbers of each of these boxes. What do you mean? The address of each of these boxes, where they begin. And it could be anything. It could be, this one could be 500, this one could be 1. I have no idea. I mean, I have no idea what they are. There's no order to them. Once I get there, then I've got the right box, but I got to know how far down to go to get to the actual right place that I want to be in memory. So that's the P2. This P1 tells me which box to jump to. It tells me jump to this box. P1 tells me, it tells me in the outer page table, go down, 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 this amount. Once I get there, there's got to be a row here which tells me the ID number of this box. Once I've got the ID number of this box, I go back. That information I got, here I can draw it. Like, here. This has some number in it, like let's do 717. That tells me go to box 717. This is how much to go down. Let's say this is 3. So I went down 1, 2, 3, and I'm here, and I got this magic number 717. That's the ID. That's the address of this box. Now I jump over here, and I look over here, and it says 4. So I say go down 1, 2, from whatever. 0, 1, 2, 3. 0, 1, 2, 3. 3. So no, 4. Sorry. 0, 1, 2, 3, 4. And then that 4 tells me to go to, memory location 812. And here's 812. And then I go back here and take the D here. And the D is 101. So I go down 0 to 100, and here's 101. That's the way it's working. I got all this, that's what it says, all these layers of abstraction.
And the point of doing this is that you can have a lot more memory because you can have a lot of tape boxes. It just allows you to put more in.
It allows me to, no, it doesn't allow me to have more memory. It allows me to have a smaller page table. Our problem was that our page table was getting enormous. If we're going to have if we would have, and remember, we have to have a page table for every process because we have no idea the size of it. If this P1 is going to work, it has to be able to reference all the possible memory locations. So we'd have very large page tables. This is in order to reduce the size of the page table. That's the purpose.
But now you have a ton of page tables. Like you now have over 717 page tables.
No, not necessarily. Well, no. So I want to point out something. All right, wait a second. First, I want to point out something. This is 717. This one could be 512, and this one could be invalid. This one could be invalid. In other words, I'm not necessarily using all the memory of the computer. Not one process is not necessarily using all the memory of the computer. Some of them are actually not valid. If I would try to go to this one, it would tell me, sorry, that memory place is not assigned to you. But my map has every single place. It's like if I would draw a map of where all the dorms are for Machon Tal in Givat Shaul. So I would draw every single building and every single apartment, and I'd put an X on, or I put a red mark in those apartments where there's dorm rooms. But I still have to write all the apartments because my map is, because maybe tomorrow I'll change it, and now girls will live in some other building, and I need to have, my map needs to encompass. My map needs to encompass all the possible locations where the memory of the program is, and then I'm just going to label the ones that I'm actually using and the ones that I'm not actually using. So I'm going to have this invalid valid bit. I'm going to have another bit here, which tells me whether it's valid or not. Of course, hopefully I'll never try to go to an address like that. Hopefully when the CPU generates this address over here, he's not going to give me an address to go to an apartment where no girls live. Like, I'm just going to, whatever, where I'm not going to deliver food to an apartment where there's nobody there. So, but theoretically, if it would happen, if there'd be a mistake in the program and he tried to jump to some memory that's not assigned to him, then I'd immediately find out here. So it's not like there's a millions of these. These ones are only, the second level page table are only ones that are actually being used. And the hour page table is now much smaller than it was before. because it doesn't refer to all the memory, it just refers to all the possible page tables there could be. Even if there's only one, it'll still be the same size. Yeah.
So the 717, is that the location where the second page table is, or is that? Like where's
Yes.
the seven- okay.
Yeah, that is where, that's, in other words, really, this is all physical memory. This is the physical memory. And at location 717 in the physical memory begins the this page table.
So it's really, is it 717 and then it counts down from there?
And then it counts down from there by whatever value is in this place here. Now, what I was pointing out is that what if, this is really the complication, which is what if this is not 1 byte, but it's 2 bytes. So then if I want to go down to the 4th row, in other words, if this is, so if I want to go down to the 4th row, I'd have to take this number 4 and multiply it by 4 and go down to 16. Or did I say 2 would be 8. If I want to go to the 4th row, each one of these is divided up into 2 bytes, then this number, you're gonna have to multiply it by something. But, or another way to put it is, I have to have a larger range.
Won't we know? Like everything's gonna be implemented at the same time, kind of, so you're gonna know.
Yeah, we're gonna know. We're designing this now for the operating system.
Hang on, but what does it say in the inner page, like the page table, inner page table, in line 4, what would it say there?
So what it'll say here on line 4,
Yeah.
this is an excellent question. Tell me your name for the 10th time.
Leora.
Leora.
That's the answer.
Okay, so Leora asked an excellent question. What is it saying here? Well, you answer your question. What should it be saying here? It's saying, I told you what it's saying. It's saying here that 812. Just like this says
It's
717.
saying the
This said 717, and that's what made me go here.
But,
This is gonna say 812,
and
and
then,
it's gonna say go there.
and then
but-
the P, I don't see what, a D. says
This just tells me
101.
where, this just
101.
tells me where to go to find that 812.
But D, the third number in the logical graph.
That tells me in 812 how far to go down.
Right, so 101, you really mean 5.
No, I wrote 10, 100, 101.
You don't mean 5?
Why 5?
And 3, yeah, because,
3, 4, 5?
no, not
No.
3, 4, 5. No, because then P1, it's telling you to go down 3 levels from the beginning of the outer page table, right? Then
Yes.
you find the address of the inner page table, then P2 tells you to go down 4 levels, bits, whatever it is.
Exactly. And then P, and now I've got to, then I got to this address.
Exactly, so shouldn't it tell you how far to go down?
It does. 101 is how far to go down.
Oh, maybe you're going down 101 steps.
Yes.
Say when you go down 4 steps, going
Yeah.
it's not like 5. 101.
Yeah, 101. That's why I wrote 0, dot, 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 dot,
Like
dot.
the address of it.
No, it's within, it's the offset within this place.
Oh.
Essentially wait, let's think of what I'm doing. Essentially what I'm doing is I'm taking this 812. I'm not going down, counting 1, 2, 3. I'm just taking this 812, adding to it 101, getting 913, and going directly to that location. That's what I'm doing. But now I want to point out this one more thing though, which is Leora, yeah? Leora, you asked what's written here, 812. But I want to ask your question in a slightly different way, which is actually what I thought you meant, but then I realized. But let's ask the question in a slightly different way. How many possible numbers can be here? Now 0 could be there, 1 could be there. What's the largest possible number that could be here? Well, wait. No, not the end. What?
2 to the D.
Notice how many digits do I need to have here in order to address all these possible boxes? Well, how many boxes are there? That's the first question we have to know. So if we this picture doesn't show any numbers, but if I go back to this picture, we see here that what do we see here? We see that the size, first of all, the size of memory is 32 bits of addressable, this is how we're going to refer to it, addressable memory. Right? That's how many bits we have. That's the size of our memory. And how big is each page? Well, if the page offset is 10, then each page is 10. So the page offset, so the page size, what's 10? 2 to the 10th
So that's a kilobyte?
is a kilobyte, 1 kilobyte or 2 to the 10th. Okay, so let's go back to our other slide. That's the information that we just got. So if our page size is 1 kilobyte or 2 to the 10th, how many of them do we have in 32 big? Well, it's very easy, right?
Or is it 2 to the 12?
No, 2 to the 22nd.
Oh, you combine the two numbers?
Well, because I don't care about that right now. I just care about the page size is, that's why I say always start from the offset. The page size is 2 to the 10th. That's the size of the pages. And I know that the amount of memory I have is 2 to the 32. So how many must I have of those blocks of 2 to the 10? Must be that I have 2 to the 22nd, right? So how many bits is that? To reference all of these pages, all of these 2 to the 10th pages, all these pages of size 1 kilobyte, how many references do I need? How many bits do I need? Easy question.
22.
22. I must have 22 bits.
You just lost.
I just lost you.
Me too.
Okay,
Because when you're saying page size and then 2 to.
put it this way. If I,
That's 2 to the 22 pages? Or 2 to the
wait,
22?
let's go, let me go back. Let me go back. If I have 32 bits of addressable space, how many, we know we should, in our mind, we know that that's 4 gigabytes of memory. 4 gigabytes takes, why 4 gigabytes? Because to the 30th is a gigabyte. 2 to the 2nd is 4. So it's 4 gigabytes. This is 4 gigabytes of memory. 4 gigabytes of memory takes 32 bits to reference every single byte. That should be known to you, right? Every byte has a number on it. This you should have known from the class with Avi. On every byte has an address. So if I want to be able to address any possible location, I need to have a number for each one of those, an ID number for each one of those. The first one is 0, the second one is 1, until the last one is 2 to the 32. And that will cover 4 gigabytes of memory. Right? That's what 32 bits. 32 bits is because I have 2 to the 32. Now, if I say, so that means my memory, the address size to address every single one is 32 bits. But if I say, I'm going to just address them in groups in apartment buildings instead of each individual, apartment, let's talk about apartment buildings. Let's say each apartment building has in it 2 to the 10th apartments. So it has in it 2 to the 10th apartments, which is a kilobyte. It has a 10 to the 24th, let's say 1,024 apartments in each building. So now how many addresses do I need to give apartment buildings? That's our question. If I have the same number of apartments, I still have 4 giga apartments. But now I've grouped them into apartment buildings. And now I want to give a number for each apartment building, not for each apartment, each apartment building. How many apartment buildings am I going to have? So it's very simple. I take 2 to the 32 divided by 2 to the 10th, and that's how many apartment buildings I have, which is 2 to the 22nd.
Subtract.
I subtract. When you divide, right, when you divide powers, you subtract the power. So if I have 2 to the 32 divided by 2 to the 10th, I get 2 to the 22nd. So that's how many apartment buildings I have. So how many numbers do I need to give each one? The first one to be 0, second one 1. I'm going to need 1 for each building. Well, that's this number. That's how many I have. I have 2 to the 22nd. That means I need 22 bits. 22 bits. The first one will be lots of zeros. Second will be lots of zeros with a 1. And the last one will be all ones. And that will be referencing, it will be giving a number to all the apartment buildings that each one of them has 2 to the 10th. Now I can just say, go to apartment building, 1 and go to apartment 1. So where is that actually going to be? Well, if we're starting at 0, so apartment building 1 will actually be, it won't be the first apartment in memory. It'll be the 2 to the 10th apartment. It'll be 1,024. And then I said 1, so it'll be 1,025. So byte, the way I'll get to byte 1,025 will be by saying, go to apartment building 1, byte 1. So I'll move over 1 apartment building, we'll go to apartment building 0, I'll go to apartment building 1, so I'm already after actually be plus 2, whatever, it doesn't matter, yeah.
So then the outer page table corresponds to all the buildings, and then the inner page table is each individual building, and then the last one is each apartment within a specific building.
No, not yet. Wait, I'm building up to something and no, I don't think, no, this is not this number, wait, let's start with the last one. I don't want to talk about this one. I just want to talk about this one. This number is 812. So fine, this is apartment building 812. This is the apartment building. This is apartment building.
So also the offset tells you which apartment.
This is the apartment building 812. But according to what I just, so in order to write this 812, I'm gonna have a lot of zeros and then eventually a bunch of ones to get to the number 812. But I don't want to think about, so I'm gonna write just 812 here in decimal. But it's really think of it as it's in ones and zeros in binary. But my question is how many bits, so these zeros, how many zeros do I have before it? In other words, I need to be able to get to apartment building 1. So the size of this row has to be how big?
22.
It has to be 22 bits. It has to be 20 bits. Plus it has to have another bit for invalid, because it could be I try to get someplace and somehow I'm not allowed to go there.
Wait,
So
is
let's say
that
23 bits. It has to be. So yeah. So I'm just pointing out a problem. I'm pointing out a problem.
Is there always a valid bit?
Isn't
Yeah.
the invalid,
Theory, okay.
No, there's a.
there's invalid in all.
We don't
of
really
the
care about
tables.
one bit. We're gonna, because they always gonna be bytes. So you know what I mean? We're not gonna give you exactly 23 bits. It's gonna be divided by 8, and we're gonna figure out how many bytes it is.
I thought the page table had no invalid. Only the outer page table had invalid.
Yeah.
Only the outer page that was invalid? Okay.
That was the
If-
point.
Fine, let's say like that, fine, you're right. I agree with you. It's not important to me. At the moment, for what I'm trying to explain, it's not important to me, whether there's an invalid bit or not. But let's just say we were here, yeah. Let's just say that it's 22 bits. So this row has to be 22 bits. 22 bits. If that row is 22 bits, how many bytes is that? 4, because 4, because 8 and 8 is 16. No, that's 4, 3.
We need 3 plus,
3. 8 and 8 is 16, plus another 8 is 24. So 24, so I'm gonna need 3, I'm gonna need 3 bytes, and I'll have a little extra space. So 3 bytes. But wait a second. If this is 3 bytes,
we have to multiply.
well, let's make it 4 bytes. Let's just make it 4 bytes to have everything be multiples of 2. Because 3 bytes is going to be weird mathematically. Let's say 4 bytes. If this is 4 bytes, and we know that these boxes are the same size as these boxes, right?
Wait, which boxes are the same size?
All these boxes are the same size because they're pages. Because remember, the memory is page. We're always
But the little box is a page, the box is a page.
Even.
no. The page table is everything is page. We never get
But-
contiguous memory.
But everything.
We have a system where we don't have contiguous memory. We have always our memory is in.
So I'm
What's the gray and what's the blue?
right.
The gray is in this case, the gray is the one we're actually interested in.
So it's a page?
No, it's a row in a page table.
Right, that's not right.
It's a row in a page table.
So,
But I'm
one of the
saying,
isn't.
I'm pointing out that the row in the page table has to be 4 bytes long.
right, that,
Yes, it does. It has to
so
be.
what?
The row and page table.
That's all I'm saying. That's all I'm saying. Now I want to go one step further.
But the outer page
Every-
table isn't a page, if the outer page table is a separate
It's a
table.
little bit confusing.
But
Yeah.
the outer page table is
It's a lot
a page, it's a table, on the page of the page table and then the actual memory, those are pages, the outer page table. That's the whole point, that you have, you're splitting up the
Every,
page table.
there's no memory that's not in, oh, you're saying it's in, there's no memory that is not paged. We are now in page memory. We
Then
don't,
what's the
remember,
outer?
there's 2 choices, either contiguous memory or page memory. Everything is paged.
So every row is a page.
Oh, you're asking, how does you're asking,
How could it be the same size if the outer page table is itself a table, but then the inner page table is just a table with pages in it?
yes, this is oversimplified. I'm showing the complexity that's really here. But you're right. You're saying in order for this P to work, this can't be larger than a page. Because how this is contiguous, this is assuming it's contiguous, and yet this is 12 bits. I'm just putting it as a problem here. Really. You're right. In order for this P to work, in order for me to be able to go down rows and count here, this must be contiguous. That's what you're saying. Zava is saying this has to be contiguous, otherwise this won't work. It's like this has to be
Well,
contiguous.
each page is contiguous, you can't, it within the page has to. be
Within each page has to be contiguous. But this, so I'm just pointing out the sizes of these pages. I'm working from the end backwards. Zava's already over here thinking about this one. And this one is true, we're gonna have a problem here too. But I want to talk about this one first. That's where I was. I want to talk about this one. Just realize that has, let's say it's 4 bytes. It's gonna be 4 bytes or at least 3 bytes. Or 2.5, whatever. It's gonna be more than a byte. So let's say it's 4 bytes. So this page table is also 1 kilobyte. It's also this page size, 1 kilobyte. So how many? So wait a second.
But we were, that's 2 to the 12.
So actually, we'll say it like this. We'll say it like this. So therefore, how many numbers do I need to have here? 10. Right? I need to have 10 numbers. 2 to the 10. 2 to the 10. 2 to the 10. That will refer to every single byte here. But what are going to be valid bits? I'll say it like that. I'm going to say it now a little bit differently than I thought of saying, which is if it's 2 to the 10th here, this is 10 bits, then some of these numbers will be invalid. Wait a second.
Because P1 has 12 bits and
No. P2, right? P2 is telling me how far to go down. I can never go down 1 byte or 2 bytes. I can only go down 0 bytes, 4 bytes, 8 bytes. So some of these numbers are invalid. They shouldn't be ever a number, right?
No, but we're only right in the beginning, we're saying something like, if it was 4 bytes, then we have to multiply it by 4.
Yeah, I would say that's another choice. Just saying we have this issue to deal with. Either,
Right at the beginning, you said, right in the last slide.
No, but we're doing one.
yeah, but that was assumed. What?
Here we're doing 1 byte, you said, in the thing above it. You said.
Yeah, I know. I said, you're right.
Sure,
You're right. Assuming each row in the table is, see, the book didn't get into these complicated details, but it's gonna affect us later. The book, notice if we assume, you're right, maybe I should erase that. A 10-bit offset. We must have a 10-bit offset, even if we don't have, the truth is, even if we don't have a 1 bit, even if we have 4.
That's where I got confused. You said that if it was more than 1 byte, we'd have to multiply by 4.
Right.
Now you're saying it could be more than 1 byte
And we wouldn't multiply by 4, but we could just throw them away. That would be the other alternative. We could just say, this number has to be either 0, 4, or 8. Or this number could be anything, and we just multiply by 4. But if we did that,
We'll have to know that.
then the system would have to know that. We have to have some hardware to multiply by 4. We'd have to actually have hardware to multiply by 4. We're not going to do it in hardware.
numbers. So they could be any
Right.
number, but you just.
Yeah, so forget that idea. I just sort of threw that off at the moment. I was thinking about it. That yeah, you can theoretically multiply by 4, but we're not going to do that. We're not going to multiply by 4, and we also can't really assume that each row is 1 byte because it's not going to be 1 byte. So it's really the solution is going to be to have these numbers jump by 4s.
Except for all of them, or just for the two?
Well, then we're going to say, well, what's the size of this? What's the size of these rows? We just calculated the size of these rows. What's the size of these rows?
Like, that was my question earlier, because how could it, if you said all pages are the same size, but how could it be the same size as, how could the outer be the same size as the inner?
Well, wait a second. How many of these are there? Let's start like that. How many of these are there?
Are there 2 to the?
Just like we asked how many of these are there, and we said there's 2 to the 22nd. How many of, these ones?
Are there 2 to the 12, because
You're-
P1 is 12 bits?
That's interesting. Wait a second. Maybe it's also 2 to the 22nd.
But but then how's it possible?
Wouldn't there be also?
There's 1 for each.
Because we don't know where these are. These could be anywhere in memory. These could be anywhere in the computer memory. So there's also a possibility of 2 to the 22nd. So these will also be 4 rows. Right?
But how?
We don't know where this is going to
Well,
be.
where are those bits coming from? Because if you gave 10 bits to the offset, 10 bits to P2, they only have 12 bits left.
And we can't reference all the memory, you're saying.
Yeah,
That's right. This is the problem. In other words, if we're throwing away bits over here, we're saying we're all even without talking about this one, just talking about this one. We're throwing away bits over here, then how will we ever get to every memory location?
They multiply by 4.
That's why I said multiply by 4 makes a little bit of sense. Well, all right. Let's go back to what the slides are. I'm just showing you a little bit of the complication here. So maybe now we can understand better the next slide. Assuming each row in the page table is 1 byte, that's what I was saying. Now, even 2-level paging scheme is not sufficient. Why? If a page, so here's this thing, so a page size is 4 kilobytes. Now we're saying it's not 2 to the 10th, but 2 to the 12th. Okay, but we're still talking, and we're talking about a 64-bit logical address. So let's take this example. Or how should, let me go back. I'll erase.
What was the resolution of that whole discussion? That we are confused and we don't need to know?
Yeah, we're confused. Yeah, the resolution is that we were confused. Yes, yes. And we don't really know. Well, maybe, well, let's see what they do over here. Yeah, that was the conclusion, that we're confused here. If page size is 4 kilobytes. So we have 64 bits. So here's our memory. And we have a page size of 0 to 11. That's our page size. So how many pages do we have? Let's start simple, right? How many pages do we have?
2 to the 12.
It's 60.
21.
It's 2 to the 64th divided by 2 to the 12th. Should be 2 to the 52nd. True? 2 to the 52nd pages. For
This is-
each page.
But this is a page
Pages.
for pages of what? though?
Pages of memory.
But then you have an inner table and an outer.
Forget about
table,
that.
so-
I'm just talking about the memory. Once,
No, that's how many
once-
pages you have in memory, that's what the.
some of those pages of memory will be the page table.
But memory refers to like an address, memory refers to everything, like.
I mean, wait, I want to go back to what you said. You're right. I think I take back a little what I said. I said that everything is paged. Maybe our conception is that the operating system will page all the memory except its page tables, except its page table, its outer page table. Because right, we want that outer page table to be long. Right? I guess we won't page everything. So there'll be some reserved memory for the operating system. That must be the conception, that first outer page table is not paged. Because we don't know how big it's going to be, very large, might be large.
So 52 is referring to the inner page table, and then
So 52 is ignoring what the operating system itself takes up. The operating system itself maybe uses a certain amount of memory, but by and large, all the memory needs to be paged. And therefore, if all the memory is 2 to the 64, and we're chopping it up into chunks of 2 to the 12, then we must have 2 to the 52 chunks. That's just math.
I understand the math, I'm just trying to figure it out, like where conceptually in like that table, like we'd have these numbers.
In other words, where would we have these numbers?
Yeah.
This is the page number.
And then you would split that into P1 and P2.
This is the page number, and this is the offset.
Okay, so that's
That's the D and that's the P. Right? That's
Back
the
to 1P?
offset. What?
we're back to 1P.
Well,
Okay.
no, that is the page number. Then we're gonna then divide this up. We're gonna start playing games with this P.
Okay.
But still, you're right. I mean, yes. That's if it would be 1P, then it'd be like this. There certainly are 2 to the 52 pages of memory. And that's what it says. And the page table has 2 to the 52 entries. If we'd have one row, we'd have a page table with 2 to the 52, which is obviously,
You're saying if there was 1P.
if there was one
That's how many-
page table, then it would have 2 to the 52 entries.
Okay.
One with the number, and each row would be this length, right? It would be 52 bits.
52 entries and 52 bits.
It would be 2 to the 52 entries, and each
Row.
entry rows, and each row would have In other words, it would look like this. It would look like this: 0 to 2 to the 52 minus 1, right? And then this row would have in it the ID of some place in memory, not necessarily the first place. So it could be, for example, 1 0 1 0 1 0, etc. How many would it have to be to identify all of these 252 pages? It would have to be 52. So it'd be 0 to 51 bits. So it would be very large. It would be, which is how many bytes? Again, it's like
Wouldn't it be only 12?
what? We have 7 bytes times 2 to the 52 minus 1 rows. And we would say, if I want to go to page number 0, in logical memory, you got to go to physical memory 1 0 1 0, what's it? So this page table would be how large? It would be 2 to the, wait, this is.
Why would that be 7 and not 12? I mean, why would that be 52 bits and not 12 bits?
Because we're defining the size of the number of apartment buildings, not the number of apartments. That's how many groups of bytes we have, where each group is
Right,
12. Is 12. So how big would it be? It would be 7 bytes times 2 to the 52 bytes. So it'd be whatever, 2 to the, it would be just trillions of bytes, whatever. It would be a very large number. Just 2 to the, it would be just a huge amount of bytes. Take up a ton of memory to have all of that. And in a 2-level scheme, that was all 1-level scheme. In a 2-level scheme, the inner pages could be, and here I wrote like, maybe I'm confusing myself, but I changed the slide here. In a 2-level scheme, the inner page tables could be 2 to the 10th, each one. In other words, I'll have like, each one is size 2. Why did the 2? Oh, 2 to the 10th. Why did I write 2 to the 10th? 4 byte entries. Because I still want to fit them into this, because remember I said that it's 12, 0 to 12. Right? It's 0 to 12 is the size, which is if I do 4 bytes per row, and I have 0 times 2 to the 10th minus 1 rows, then that's this equivalent to 2 to the 12th bytes, right? That's 2 to the 12 bytes. So that's the size that I said the page tables are. So in a 2-level scheme, we could have the inner page tables each be paged and be 2 to the 10th 4 byte entries. We are assuming each row is 4 bytes now. And since we must fit this into a 4 kilobyte page, we're left with only 1 kilobyte 2 to the 10th rows. And then I wrote, we'll need to append 2 zeros to every address we retrieve from P2. Is that right?
Wait.
I'm not sure if that's
But
right.
I thought that was backwards for a second, hold on. The 2 to the, we have 2 to the 12 for the offset. But isn't it, we have 12 bits for the offset, but isn't that because there are 2 to the 12 rows, you're saying that there are 2 to the 10 rows? And what the picture you drew of 0, 2 to the 10, what's that a picture of?
Of the inner page table.
But the inner page table has 10 bits, not 12.
No, the inner page table has 12, is 2 to the its size as a thing is 2 to the 12th.
And the size.
But the number of rows that it's going to have is smaller because I'm going to make each row be 4 bytes long.
Also, it's still the same size, you're just condensing it to.
I'm just,
have
instead of
the-
drawing it vertical, yeah, and then each row, so what's each row going to be? What's on a row of the inner table?
The
It's
memory address.
the address of
each page in memory.
of each page in memory. But what is the size of each page in memory's address?
10. Oh,
No, the
Well,
address
no.
is 52 bits long. Isn't it 52 bits long, the address? Because remember we said, so we just got through saying 64 bits, we divided, each address is 52 bits long. Can we fit 52 bits into 4 bytes?
No.
No, how many we have to add to, so that's, so how, why? What's
There's
that?
that three
I need
bytes.
7.
We have to what? It's 52, so 4 bytes is what, is 8, 16, 16, is 32, we need that,
You need 7 bytes.
We need 7.
We need
So
7.
it's
That's
three.
56.
so we need to add, so that's what I said here. We need to append, I don't know why I said 2 zeros to every address.
Wasn't that multiplying by 4?
Yeah, but we don't need to append 2 zeros, we need to, now these address, this is not gonna work. I mean, maybe I'm just showing you there's a certain problem here, because how are we gonna fit the address in there? You see what I'm saying? This row is gonna have to be
You need 2
more,
rows.
it's gonna be it's gonna have to be 8 bytes long, and we're gonna have 2 to the 9th. No, yeah, 2 to the 9th.
So then P2 would be.
It's gonna have to be
9
like
instead
that.
of 10,
What?
so then P2 would be 9 instead of 10,
P2,
because right now P2 is 10 because we condensed it. To be all, instead of being 2 to the 12 rows, like to match the offset, we made it 2 to the 10 rows, but each row has 4 bytes, so it's still the same amount of data as actual memory, it's just arranged differently, so then if we're making the inner page table 9 rows instead of 10, then shouldn't P2 be 9?
yes,
And then you'd have that, and then you'd have P1 be 43.
yes.
How does 9?
In other words, this really should be 9, she's saying, because I was saying incorrectly, that in order to get this address to be the actual address of a place, it has to have 7 bytes, we'll make it 8 bytes. And then I only have, how many do I have? I have, well, it depends what I'm doing with this. Depends what I'm doing with this 9. Am I multiplying it by, in other words, the number of rows that I have is 2 to the 9. But the size of memory is still 2 to the 12, so then it should be 12.
Where do we get 2 to the 9 from?
Maybe it should be 12. Maybe we should leave it as 12. Maybe it shouldn't be 9.
Well, that was the whole question we had on Sunday, that why is it 10 and not 12? So if we should just have it from to begin, just have 1 byte per
It should
row.
really be 12. I don't see, it should be 12. Because that's, we need to know where to go. Is it here? Or is it, this would be, what is it, 0? This will be 8, 16. And that P2 is telling us that. And it's gonna be, but then it's gonna have holes in our memory. Anyway, this is more of a conceptual idea. I don't, maybe,
Where did the 9 come from?
where did the 9 come from? Because I was trying to keep this 10, that was the image that the book had. So I was trying to keep that 10. But if we keep that 10, why did the 9 come?
Shouldn't it
Because,
be 2 to the
no,
5?
because it's 2 to the 9th here now.
Why?
Because if the rows are 8 bytes long, 8 bytes long,
You lost the row.
then, right, then if I have 2, that's 2 to the 3rd. That's 2 to the 3rd, but the whole size is 2 to the 12th. So how many rows of 8 bytes long do I have?
Oh.
2 to the 9th.
Okay.
2 to the 9th. Right?
Mhm.
Because I subtract.
Yeah,
So I have 2 to the 9th rows of 8 byte long, and they're all still 12, 2 to the 12th size.
why is it 8 bytes again, not 7?
Because I don't want to deal with numbers that are not multiples of 2.
Okay.
We're always going to be 4, 2, 4, 8.
How do we know that the size is 12?
They said
That was just a
page
given.
size,
That was
they
just a
give
given.
it.
If the page size is 4 kilobytes.
So in the end, we did come to the conclusion that P2 should really be 12, not 10.
Yeah, I think so. I think you're right. It has to be the same, because how else could it work?
Because if it wasn't 12, then you would have more than 1 byte per row, that would cause more problems.
Whoa, more than 1 byte per row?
Because it has to be the same size as the actual memory then. If it has, the page size has to be the same. If it has to be, a page size has to be 4 kilobytes, it would need to be 2 to the 12th, right? The inner page table. So the inner page table is, if it said the whole thing is that the page table is page, then each page
Right,
This is 2 to the
exactly.
12,
The inner page table,
to each
the
one.
outer page table maybe isn't page, but the inner page table for sure is page. That was the whole point of it.
Otherwise, then if
And
all
once it's
pages-
page, it has to be the same size as that. I don't see how it can be different.
Just that's what I'm saying, so are they just saying that there has to be more than one byte in a row in order to make it be the same size because each 2 isn't 12? And that was what you were showing how.
Yeah, maybe what they're thinking, yeah, maybe what they're thinking is let's give it. This is what I was trying to say at the beginning, maybe what they're thinking is let's give it 10 bits, but the size of this thing is actually 12 bits, is still 2 to the 12th. And we're gonna multiply those addresses by 4. You see, that was the answer that I gave before. Maybe that's what it's thinking. That, in other words, if the addresses that we're gonna get from this address are going to be, the addresses that we're gonna get from this address are gonna be in a range from 0 to 2 to the 12th. No, sorry, 2 to the 10th. But we need a bigger range. We need them to go to. Wait, sorry, am I saying that right? I have to think about it more, sorry. I did think about it and I thought I had it all clear. What is this 10? Because we're multiplying by 4, and so that is really multiplying, we're at. Yeah, you have to have. Right, well, whatever, I was, yeah, whatever, I don't want, we can't talk about it anymore. We can't talk about it anymore. It's too confusing. The only point that the book is trying to make here is that we're still gonna end up with an outer page. Even if we do it like this, we'll have an outer page table of 2 to the 42 entries. And then it says, and each entry must be 8 bytes long to be able to specify every inner page. Because there's so many inner pages. This means the total size of the outer page is 2 to the 45th bytes. Because there's this many entries and they're each one 8 bytes, so that's 2 to the 45th. So one solution is to add a second outer page, just keep going. Make more and more layers of jumping. But in the following, example, the second outer page table is still 2 to the 34th bytes in size, which is very large. And possibly 4 memory, and it'll take possibly 4 memory accesses to get to one physical memory location. In other words, you have to jump. To get the actual address, you'll have to keep on reading and reading and reading. So this is not such a good solution. Yeah, here is the example here, 12, 10, 10, and 32. Okay. So another solution, let's go on to another solution, maybe, yeah. Another solution is a hashed page table. Do you guys know what hash functions are? No? Yes?
We do it next
Somewhere
semester.
somewhere else.
What? You saw it somewhere else?
Yeah.
You do. Basically, a hash function is some kind of mathematical function that gives me another number. That's the simplest way to think about it. Just I put in one number and I get out from a black box a different number. But the special thing about it is that it's possible that 2 numbers can give me the same hash. 2 different numbers.
Hash that doesn't.
In other words, it could be some mathematical function that I put in 7 and 25, and they both give me the same final number.
A hash is always a different mathematical equation.
A different number?
Like I'm saying, for each, like whenever you do this certain function, it's
Here.
some kind of random.
No, it's not random.
Like
No.
I'm saying, you put it in, or it's something that's already like programmed.
Here. Let's A hash function is any function that can be used to map data of arbitrary size to fixed size values. In other words, I'm going to get a long number and I'm going to put it in and I'm going to get a small number out. The values returned by a hash function are called hash values, hash codes, digests, simple hashes. The values are usually used to index a fixed size table called a hash table. So here, what's this example? Right, the names, look, I see, are sometimes very long, Sandra D, and it's going to bring me to row 14. That's a simple kind of hash function.
Which is like a mapping.
Yes, it's a mapping sort of thing. But the question is, well, okay. Use of a hash function to index a hash table is called hashing or scatter storage addressing. Hash functions and their associated hash tables are used in data storage and retrieval applications to access data in a small and nearly constant time per retrieval. They require an amount of storage space fractionally great. That's not important. The use of hash functions relies on statistical properties of key and function interactions. Okay, that's the basic idea of a hash function. You see, it's a huge topic. If you're interested in hash functions. So what are we going to do with this hash function? So a hash table. So we use this when the address space is larger than 32 bits. What do? The virtual page number is hashed into a page table. In other words, we take the page number, the virtual page number, and we put it through some function and get another number out, which will be smaller. That's the main point. We're starting off with a 64-bit number, and we're going to throw it into this hash function and get out a 32-bit number, for example. This page table can, and that'll take us to some row in a page table. But what's going to, if you think about that, if you take a 64-bit number and you go to a 32-bit number, there's a lot more 64-bit numbers than there are 32-bit numbers, right? So that means, everyone agrees with me that there's a lot more 64-bit numbers than there are 32. So how can it be that I take a 64-bit number and get a 32-bit number? Which number will I get? Well, I'll just chop off the last 32 bits and use that? Well, I mean, that could be. But the point is, if I would do that, that would be the simplest hash function. Just ignore the first ones and just take the last bit, the last ones. But then what's going to happen is I'm going to get multiple inputs that are going to produce the same output. However you do it, whatever method you do with your hash function, you're going to get the same results for multiple inputs because there's a lot more inputs, possible inputs. Like in the example I did of Sandra D, there's billions of possible names. If every name works, then more than one will produce 14 because I only have a finite list of possible.
So you do produce a hash algorithm.
Yes, I use a hash algorithm. Whichever one it is and however it works, it's not important. But the point is I put in a big piece of the sausage and I get out a small piece of sausage.
And the point is to get it the most accurate so that you don't
want to keep getting the same one, but you'll get different ones for different numbers. But my main point is you'll get sometimes the same number for two different addresses. So that's the next point here. This page table contains a chain of elements hashing to the same location. So in other words, I'll get to a place in my page table, but there'll be a linked list there, and like in this picture here. In other words, this my hash function, I'll take my P and I'll go to this hash function and it'll produce me a linked list, which could be infinite. You know what I mean? We don't know how long it is, some kind of linked list. It'll point to some place in memory, which is going to have a linked list. I mean, I guess there's got to be some limit on the size of that linked list also, because Otherwise, we have a contiguous memory problem again, right? That was our whole point. It has to be that's also, but I'm getting more complicated to be. The point is, we're gonna have a linked list here to dealing with all the possible numbers that, and then it'll also be a small list. This list will be small. And then what we're gonna do is, let's say the first one that I got was this set. It's each one is going to be 3 parts. Each item in the linked list is 3 parts. The third part of each item is obviously a pointer to the next item. Every linked list has to have a pointer. The first 2 parts are a Q and an S, or sorry, are 2 numbers, 2 sets of numbers. Forget about Q and S. This number, it has to be the same as this number.
Which one?
The P. In other words, we take a number like, let's say, I'll change it from numbers to fruits. We put in banana and we come to this list, we come to this row. And the first thing we see here is apple. So we say, that's not what we're looking for. Then we go to the next one, P, oh, it's banana. We found what we're looking for. Now we put in banana, we got out a marker to this location. We get we go through those linked lists until we find the one that has the banana, that has the address that we actually put in, the initial address. Because remember, there's multiple addresses that can go in that can produce that same row. So now we have to search everything at that row till we find the one we're looking for. We found the one we're looking for, we grab the R. What's the R going to be? The R is going to be the actual physical location. And that we're going to put here, then we're going to append the D from the logical address, and that'll be our offset. So that's a nice system.
Wait, so what does that mean? Does that mean there are multiple rows in the hash table that each have a list?
Yes, every hash table is actually a pointer. Every entry in the hash table is a pointer to a place in memory where there is at least one physical a logical physical pair, address pair.
Because I'm just confused because if we're looking for P, why don't we just go straight to a linked list? So what do we need a hash table for?
Oh, because, okay, good question. Zahava asks, why do we do this? Why don't we just have a linked list of all the places we want to go and just go through the whole linked list? So what?
It's still shorter.
What?
It's still shorter because you could double up on some of the,
It's, what do you mean shorter?
like it requires less space because you don't need one per.
No, it's not going to require less space. We get one huge long linked list, and just to go through that. But what's the problem? Huge is the problem.
But then, so then
Big
what?
What's the problem?
So then how is the hash table split up? Like there's a linked list.
Wait,
for this group hash-
you're going ahead. The answer to your first question is that it would be too big. The linked list would be very long, and to search a linked list, like you know from your data structures course, is not ideal. You don't want to go through every single one. That's where we have binary trees and all kinds of things like that. But it would be too large. So what we do here is we have a table pointing to many linked lists. And hopefully those linked lists, each one is maybe 2 or 3 elements. Searching 2 or 3 elements is not a problem.
So then how do you know which linked list to go to?
By our hash function.
Um,
We throw our banana into our hashing machine and it comes out a cucumber, or it comes out whatever, it comes out some number, and that takes us to a certain row in our hash table.
And then once we're there, we
That's
check
here.
which one matches because there's more than one thing saved in each with the hashes maybe.
Exactly. The point is exactly.
So that's just
Since
less to check.
exactly. So it's just less to check. Just saves. We cut down on the amount we have to check by some huge factor. It's kind of like I don't know if you do this in data structures. If you talk about hashing, you probably should have.
we do next semester.
So now I give you a little sneak preview into that, because this is a very interesting way to do a binary tree. It's like a binary tree, but instead of being a binary tree, it's essentially, if I would draw it, a binary tree is, it's like, oh, my marker's not good. A binary tree is, like this, and the problem with a binary tree is that sometimes it can look like this, it'd be lopsided. And then it doesn't really help you so much as it could. Whatever, it could be like that. So the hash table idea, if we would draw it graphically, it would be something like that.
So the genealogical address
So-
maps as something in the hash table, which maps as something in the linked list, which
Well, say it again.
the genealogical address mapped.
Goes
maps as
here,
something
produces,
in-
does some computation, gets me to this row,
So some kind of row in the hash table, which,
which then links to a linked list.
and it knows which one because,
Well, it could be that it would take, if I put in instead of P, if I put in P1, then it would take me to here, and then I would go to another linked list. with
but I'm saying, how does it know which link in the list it needs? Like,
Because it compares this P to this P.
oh, okay.
It has to find the same occurring key. In other words, this is a key. The key is P. P goes into the hash function and produces an output. The output takes you to this row. Then I'm going to search again for that key. I'm going to use the key twice.
You also just explained the D.
The D part is what we always have, is that we take whatever our logical address is and we create an offset based on the size. Remember I said that's always the one you can know. We create an offset based on the size of our pages. That's the size of D, the number of bits. And we ignore that part. We just take the rest of the address and put that through the hash table. But we can't just ignore that forever. We bring it back over here and stick it onto the, when we found our P, really what we're interested in is the R that was associated with it. We got that R, and that's the frame that we actually want. And then the offset in the frame is our D. We're done?
Yeah.
Yeah. So that's hashing. Next time is inverted page tables.
And then the D is the building that we want. in here, or is it the apartment?
No,
Thank
D is
you.
the apartment. Sure.
Thank you.
Is there only one more slideshow after this one?
No.